Welcome back to Chapter 3 of An Introduction to Earth Science. Of course, we're using the textbook Foundations of Earth Science, the 8th edition. That's by Lutgens and Tarbuck. And this is Chapter 3, Landscapes Fashioned by Water. So we're going to talk not only about rivers and streams, but about groundwater and the erosional effects of groundwater and how groundwater impacts streams and rivers that we see on the surface. We're going to talk about a lot about landforms that develop as streams move from their headwaters down to their mouths, about base levels and deltas and floodplains and flooding. So there's lots to talk about in Chapter 3. Often in this course, we will start by defining the types of processes in play and what's powering those processes. If you recall, we have two types in earth science: our external processes that occur at or near the Earth's surface, typically powered from the sun's energy, and then internal processes that are powered from the energy from the Earth's interior, whether it's the leftover heat from the formation of the Earth or heat from radioactive decay. Those external processes that occur at or near the Earth's surface can also include weathering, which is a function of rocks moving into a new environment and trying to come into equilibrium with that environment; mass wasting, which is a function of gravity; and erosion, which is also the movement downstream of sediment. So those are our external processes that we are going to be looking at when we're talking about water moving across and through the earth. So we're going to start out with mass wasting, this external process at the surface that's largely going to be a function of gravity. And we know that Earth's surface is covered by slopes. And we should also recognize that those slopes are unstable. So gravity will ultimately cause any material along that slope to move downhill or to move downslope. And that downslope movement of material due to gravity is called mass wasting. So it may be slow, even imperceptible, or it could be completely catastrophic. And it doesn't necessarily require a medium. This isn't like erosion that requires a medium of wind or water or waves or glaciers. Mass wasting does not require a medium. It happens all on its own. So here are a couple of different examples of mass wasting. This isn't all of them, but we have a slump in the upper left in which there's a downward sliding of rock and unconsolidated material that kind of moves along a curved surface. And then we also have B, the rock slide, in which blocks of bedrock break loose and also slide along the surface and very rapidly downhill. And then we have flows that may work in a channel, like a debris flow, there, C, the bottom left. Weathered debris containing a large amount of water, and it's confined to that channel, sometimes called a mud flow or debris flow. And then there's a more widespread movement, an earth flow, which is water-saturated soil, oftentimes clay-rich, on a hillside that just breaks away and moves downslope. Mass wasting has a significant, or perhaps the largest, impact on landform development. It helps in the evolution of different landforms. Weathering breaks rocks apart, mass wasting transfers those materials downslope, erosion and transportation carries the materials away, and that sediment eventually makes its way to the base level, which oftentimes is the ocean or the sea. Mass wasting also helps to shape stream valleys, which is the world's most common landform, generally much wider than they are deep, and that mass wasting helps to increase the width of valleys. And eventually, steep, rugged landscapes, due to mass wasting in valleys, can be worn down into a much, much more subdued terrain or a gentle landscape. Here's an excellent example of mass wasting in a valley. Of course, we're talking about the Colorado River and the Grand Canyon, and you can see where this particular valley obviously is significantly wider than the stream itself. The Colorado River is just this small area here, and if we only looked at erosion and the moving of material downstream due to erosion, it'd be this narrow band inside the center of the valley that we would see. We'd see a very steep-sided canyon, but mass wasting is what causes all this other material to fall down the slopes, end up in the Colorado River, and then eventually get washed downstream toward the ocean. So it's mass wasting that turns a steep valley into a wide valley. And of course, gravity is the controlling force. Other factors that help mass overcome inertia to begin to move down slope is gradual weakening of materials The slope gets closer and closer to being unstable until some trigger initiates that downslope movement. Now, typically there's a trigger, but not always. Saturation with water from excessive rain or maybe even overwatering can be a trigger. Oversteepening of the slope, for some reason parts of the slope are eroded away, and that oversteepening causes mass wasting. There's also the removal of vegetation. We see that in many parts of the world where rainforests are stripped away for agriculture, and it results in mass wasting and erosion. And then again, other triggers can be massive vibrations caused by things such as earthquakes. So one of those triggers is the saturation of water. Water in pore spaces tends to reduce or drop the cohesion between particles of sediment and allows those particles of sediment to slide by themselves. So water also adds weight to sediment. So water does two things in terms of causing mass to overcome inertia and begin to move downhill. It reduces the cohesion between sediment particles, but it also adds weight to the sediment, and that extra weight is worked on by gravity to cause mass wasting. Oversteepening, when we have unconsolidated sediment that forms a stable slope at certain angles of repose, depending on the size and shapes of the particles, it will become oversteepened and we'll start to see mass wasting. And in the next slide, we'll show you that angle of repose. Stream undercutting can cause oversteepening, wave undercutting can cause oversteepening, and of course human activity can cause oversteepening. So the angle of repose is somewhere between 25, 35, 40%, and basically what it tells us is depending on the grain size, dry material will only be able to stack up at a certain angle, and once it gets over that angle, higher than that angle, it will slide downhill. So on this big pile of sand, we've got about a 30% angle of repose, and what we know is if we dump more sand on top of this mountain, that angle will become higher and all that sand will slide down, making the base just broader. So you think about going to the beach and you make a sandcastle in very, very dry sand. You can kind of mound it up, but you can't actually build that sandcastle. If you moisten that sand a little bit, not saturate it, but moisten it a little bit, the stickiness of water will allow you to make a sandcastle. But if you add too much water to that sand, it will just create a muddy slurry and that sand will flow away. Other triggers of mass wasting, the removal of vegetation and root systems that bind sediment. This can occur from forest fires, human deforestation, development and farming. Earthquakes can also dislodge rock and unconsolidated materials. And many mass wasting events occur without any identifiable trigger at all. It's just the slope gets to that point and failure occurs. If we are going to talk about landscapes fashioned by water, we have to start with the hydraulic cycle. This illustration, probably something you've seen since 5th or 6th grade. The hydraulic cycle, the movement of water between the ocean, the atmosphere, and the land. And we're talking, of course, about one of the spheres of the Earth system, the hydrosphere. And the hydrosphere represents all of the reservoirs where water is held. Oceans, glaciers, rivers, lakes, in the air, in rock, in soil, and in living tissues. Water evaporates from the sea, it condenses into clouds, precipitation allows it to rain both over the ocean and over land. Runoff may occur, infiltration into groundwater may occur, evaporation as well from the land, and transpiration, that's going to be plants giving off water. This is all part of the water cycle and all part of this movement of water through the entire hydrosphere, but also interacting with the other spheres, the biosphere and the geosphere as well. Of those reservoirs that hold the water of the hydrosphere, 96.5% in the global ocean. So an astounding amount of the water on Earth in the global ocean. Just under 1% is salt groundwater and lakes, so salty groundwater and salty lakes. And so there's only really about 2.5% of all the water on Earth that's fresh water. Breaking that 2.5% down, you have about 1.72% in glaciers, about 0.03% is all other fresh water, streams, lakes, soils, moisture, atmosphere, and then about 0.75% in groundwater. So of all the fresh water on Earth, really, we all know that a massive chunk of it is in the glaciers and the ice, but there's also just a significant amount that is in groundwater, just a tremendous amount of the water in groundwater, of the fresh water. Really very little of the water is in the atmosphere in terms of all the water on Earth. I mean, there's a lot of water up there, but in terms of all the water on Earth, not a whole lot of it is actually in the atmosphere. So this whole hydraulic cycle is powered by the sun. Water enters the atmosphere from the oceans via evaporation, Then you get some complex processes we'll talk about later in the course that produce condensation, cloud formation. And then the winds move those clouds to the atmosphere. Precipitation is going to fall in the ocean or the continents. And essentially, the hydraulic cycle is balanced. We have as much evapotranspiration as we have precipitation. The precipitation exceeds the evaporation over land, and the evaporation exceeds the precipitation over the ocean. Of the water that falls on land, you have infiltration and runoff. Infiltration is just water soaking into the ground, percolating into the ground. And runoff is, well, water running over the ground. So you get runoff if you have a high intensity or high duration of rainfall, if the soil is already saturated, the nature of the surface material, if it's a whole lot of concrete, the water is going to run off. The slope of the land, big steep slopes will also cause runoff as well, and also the extent and type of vegetation. No vegetation, you may have some types of runoff, and with a whole lot of vegetation or certain types of vegetation that may control that runoff. So in addition to infiltration and runoff, once that water gets into the ground, it can be absorbed by plants and then eventually released via transpiration. So when plants give up their water, that's transpiration. When water gives up to water vapor, so just going back to transpiration, when plants give up liquid water to become water vapor in the atmosphere, it's transpiration. When liquid water evaporates, obviously it's evaporation. So we call that evapotranspiration, the combined effects of evaporation and transpiration. Now, of course, precipitation in cold regions is going to result in glaciers. So water that runs off, water that doesn't infiltrate, water that runs off is running water. And it starts as completely unconfined thin sheets across hill slopes. And then those thin sheets may develop into tiny channels that we're going to refer to as rills. Then those rills converge to form gullies. And then gullies converge to form streams and rivers that carry water from larger areas. And that entire area that drains into a specific river, so we're talking about all the area that drains into this river, we're going to call this the trunk stream, we're going to define that in a few minutes, and the outlet into its base level. All the area that drains into that river is bounded by this high ground here, and high ground here, those dashed lines. Those are the high grounds. Water falling or rain falling here goes into this drainage basin, rain falling here goes into that drainage basin. That is called a drainage divide. So drainage basins are separated by divides, and they are all the land area that contributes to a river system. Lots of different scales of that. So here's the Yellowstone River. All these different land areas contribute to the Yellowstone River. The high ground along it is the drainage divide. This whole big thing here is just this little green section, little green triangle here, that all contributes to the Mississippi River drainage basin. So the Mississippi River flowing out the Gulf of Mexico has water, overland flow, that turns into rills and then gullies and then streams from the northern United States into the Rockies, all the way to the Appalachians, coming out of, in some cases, near the Great Lakes. And all those major rivers, so we're talking about the Missouri, the Mississippi, the Arkansas, the Ohio, the Tennessee, they all drain, eventually they all connect and drain into the Mississippi, and this whole thing is the Mississippi drainage basin, which is one of the largest drainage basins in the world. So as a river system carries water from that drainage basin down to the mouth of the actual river, there's going to be three different zones. There's going to be a zone of sediment production where erosion dominates, right? This is where most of the sediment comes from. This is where the headwaters are. There's going to be a region of sediment transportation where the channel is going to move that sediment downstream, and at that point we refer to this stream as a trunk stream. It's mainly moving sediment. We're not seeing a lot of erosion in this area. And then the third section is this area of deposition, where the river slowly enters a body of water and sediment accumulates, oftentimes forming this delta, this triangular shaped delta. So water flow in slow-moving streams can be one of two things. Well, water can flow one of two different ways. It can be a laminar flow or it can be a turbulent flow. If you have water in a very slow-moving stream that's moving roughly in a straight line path parallel to the stream channel, that's going to be referred to as a laminar flow. But most stream flow, the large majority of streams, flow in a turbulent flow where water moves erratically and sometimes in a swirling motion. And this turbulent flow has the ability to lift sediment from the stream bed. And the higher the velocity of the water, the higher the turbulence, and therefore the greater amount of sediment that can be lifted from the stream bed, and therefore the greater amount of turbidity. And turbidity refers to how much sediment is actually in the water column. So this water in the stream to the left is not standing still. It's got a laminar flow. It's slowly moving toward the bottom of the picture, where very clearly the Colorado River has got a turbulent flow. So one of the things that affect how much sediment, how much erosion that the stream can do is this concept of flow. But the flow velocity of the stream is kind of an interesting thing. It changes, it varies through the length of the stream. It also varies through different time periods, different life cycles of the stream. But that flow velocity is dependent on the slope of the gradient, the size of the channel, and the cross-sectional shape of that channel. The shape has a lot to do with it. Channel roughness, which means if you have a muddy, flat, smooth channel bottom, there's not a lot of roughness. If you have a rocky, bouldery channel bottom, there's a lot of roughness. There's much more friction. So channel roughness is really a function of friction, and then there's the amount of water flowing in that channel. The factors affecting flow velocity, we'll talk about those for a little bit. Gradient and discharge here. Gradient is the vertical drop over a specified distance. How far did it drop over the distance that it dropped? Varies from stream to stream. And over this, the length of a stream. So you may have different gradients. Clearly, you'll have different gradients over the length of a stream. At the headwaters, up in the mountains, it'll be very steep. And then down by the mouth, it'll be very, very gradual. So shape, size, and roughness of the channel affect the amount of friction between the channel and the water. I mentioned that in the last slide. Higher friction creates turbulence and slower flow. And then discharge. That's the volume of water flowing past a certain point in a given unit of time, meters cubed per second. So intermittent streams only flow during wet periods, and then ephemeral streams only carry water after a heavy rainfall. So the cross-sectional view of a stream, so you got the stream coming out of the Sierra Nevada into the San Joaquin Valley, starts way up near Mount Whitney, and it's the King River. So you can see on the left, you have at the head of the river, very, very steep gradient, and then generally becomes flatter and flatter and flatter. But overall, it's a concave shape. There are some local irregularities, including what looks like a little waterfall here, but overall it's got this concave shape. The gradient, the sediment size, and channel roughness will decrease, so the gradient, okay, the steepness of it, all right, the channel roughness, it's all very rocky and rough up here at the top, much, much smoother at the bottom. And the size of sediment that can be carried. With this up here, larger sediment can be carried, and as you get down to the mouth, it'll be smaller and smaller. All this is going to decrease from the head to the mouth. While discharge, how much water is flowing, and channel size increases. Up here, the river may be very narrow, but at the bottom, it may be really actually quite wide, and flow velocity also increases. So it may seem like that river is really moving fast up in the headwaters, but we find out that it's actually moving fastest down here where it's nice and wide. And this is from the book. This is increasing from the headwaters to the mouth, and that channel slope, the gradient, and the channel roughness gets lower as you move toward the mouth, but the discharge, how much can flow through, the channel size, and also the velocity all get larger as you go from the headwaters down to the mouth. All right, so what work does running water do? Well, I often say that moving water is the strongest force in nature, and I genuinely believe that. They are massive erosional agents. Streams obviously erode tremendous amounts of material from the earth. You can see this is a very muddy stream, and that muddiness comes from erosion. Raindrops knock sediment loose. The flow of water in the stream can dislodge and lift those particles from the channel, and it just moves it downstream. And if you have bedrock, it's going to erode very slowly, but it will erode. But poorly consolidated or unconsolidated material is going to erode very, very quickly. And those, even in bedrock, you can still have enough hydraulic force to cut into that bedrock. Particularly, other smaller pebbles and rocks will move along that bedrock and actually act as like sandpaper to erode away. So here's your raindrops striking the ground perhaps as high as 35 kilometers per hour, and all that's bouncing back up are particles of sediment that have been dislodged from the soil. here's a stream bed that's moving through bedrock, but these smaller pebbles are actually abrading and cutting away at the stream channel, the bedrock stream channel. And sometimes they swirl around these spots and create what are known as potholes. All right, so when we talk about the erosional power of a stream and what a stream can do, we know that streams can transport sediment in three basic ways. There's a dissolved load, a suspended load, and then what's known as the bed load. The dissolved load is material in solution. So these are ions, this is elements that have literally been dissolved and are moving in the water. They're invisible. Most of that dissolved load is delivered through groundwater, through water percolating through the ground in the soil. And dissolved load just basically moves wherever the water moves. It's basically invisible. Now, suspended load and bed load are highly dependent on how fast the water is moving. The faster the water is moving, the larger the particle it can move. The slower it's moving, the smaller the particle. So dissolved load is not a function of velocity, but suspended and bed load are. Suspended load is a material suspended in the water. So your silts, generally your silts and your clays, that's what's going to be suspended in the water. Your really fine materials. Your sands and then your pebbles and your gravel and even larger rocks, they're going to be moving along as bed load. Now sand may move along by bouncing along. They call that saltation. Gravel and pebbles may bounce a little bit. Gravel may roll or slide. And then big rocks may just slide along the roll as well. So that's your bed load. Suspended load, bed load, and dissolved load. A stream has capacity and it has competence when it comes to sediment. Capacity is the maximum load of solid particles a stream can transport per unit time. So if more water or higher discharge is moving through that stream, it has a higher capacity. But competence is the stream's ability to transport particle size. So higher competence means it can move larger particles. Higher competence is essentially a function of higher velocity. So as flow decreases, competence is reduced and particles settle out. So this is a big part of sediment and erosion. When sediment is moving along in a medium, whether it's waves, wind, in this case water, the faster the wind or water is moving, the larger the sizes it can move. And when that wind or water slows down, the first thing that falls out, the first thing that's deposited are those larger pieces. And smaller pieces will stay in the wind or water for much longer periods of time until the wind or water just comes to a complete stop, and then maybe those much smaller particles will settle out. And this differentiation between where different sized particles fall out or deposited is known as sorting. And it separates particles of various sizes. So competence is the stream's ability to transport based on particle size, and capacity is based on essentially discharge, how much water is moving through. It's a maximum load of solid particles. Everything that is dropped out by a stream is known as alluvium. That's the material that's deposited by the stream. And with that, we have two types of general stream channels. There's really a wide range in between, but you have alluvial channels, you have bedrock channels. Bedrock channels actively cut into solid rock, and then alluvial channels are composed of unconsolidated sediment. Alluvial channels are composed of loosely consolidated sediment, continuously being eroded, transported, and then redeposited. Shape is controlled by the average sediment size, gradient, and discharge. So different sediment sizes, different gradients, different discharge is going to give those streams a different shape. Two types of shapes that you might see are meandering channels and braided channels. Now, bedrock channels, as we've already said, are cut right into solid rock. They are common up at the headwaters, up in the mountains with steep gradient. They tend to mainly transport big chunks, large particles. Bedrock channels tend to alternate between a more gentle gradient where alluvium accumulates, meaning it slows down a little bit and the particles fall out, and then steeper segments where the bedrock's being cut into. And that, because of that, rapids and waterfalls are also common. A channel pattern is generally controlled by the underlying geologic structure. So oftentimes it follows circuitous paths, winding and irregular, because it's following the underlying geologic structure. Meandering channels, different situation. Meandering channels have sweeping bends called meanders. They carry a lot of sediment. They're deep, they have smooth channels, their banks are somewhat resistant to flow, to erosion, and most erosion occurs on the outside of the meander or on the cut bank where the velocity is the highest. And then sediment is going to be deposited on the inside of the meander where the turbulence and velocity are low. That's going to form a point bar. And meanders will migrate laterally and downstream, meaning they'll go side to side and they'll go downstream. And some of the things that result from that are oxbow lakes and cutoffs. So here is a meandering channel where it's eroding on the outside edge and eroding and cutting away at the bank and depositing on the inside edge. And there you have your point bar. And here it comes around, and because the maximum velocity is on the outside of the turn, you're getting erosion happening on the outside, and then you're getting a point bar developing where the deposition's occurring. And it sweeps back around, and erosion's happening on this backside, and you have a point bar developing here. And as the stream meanders across this channel or this valley, it will widen this valley out and make it a flatter, widened valley. Now, at times of flood, the water will come up out of this bank and spread across the entire floodplain or flood valley and will deposit its finer sediments out in the flood valley. And those finer sediments are typically clays and silts, which makes them great for agriculture, which is why agricultural concerns oftentimes want to grow in floodplains. And you can see here you have a much drier area, but in the floodplain you have lots of vegetation. So the meanders will flow back and forth and migrate back and forth across the valley, but they also, on the downside, the downslope side, they have a little bit more velocity here, and they'll also begin to cut away at the downslope side of these meanders. So right in there, then right in there, and it will cause these meanders to actually move downstream as well. And what ends up happening is that meander moves right up here, this meander moves downstream and eventually cuts across that neck, creating a cutoff, and what it leaves behind is the oxbow lake. And you can see an oxbow lake here, an oxbow lake here. There may have been an oxbow, well, there was an oxbow lake here at one time, but it looks like it's now filled in with vegetation. And so these alluvial channels have these very interesting landforms that develop. And actually a pretty good indication of the age of the stream, because it's going to be an older stream to have that kind of landform. A different type of alluvial channel is a braided channel. Now, they're a complex network of converging and diverging channels. You can see them all going in and out here. And they basically form where the stream load is larger, your sands and gravels. And, importantly, the discharge is variable. At periods of high discharge, a lot of water moving, that sand and gravel move downstream. But perhaps it's because you have a drought season, or maybe it's because this is at the base of a glacier, and in the wintertime you don't have much water flowing down. When there's a low discharge, all that sand and gravel will fall out, and with that sand and gravel falling out, you get these little islands in between that are basically unconsolidated sediment, and it creates this braided stream, and called the braided stream because of it looks like braids of hair, right? So streams create these valleys, and a stream valley is not only the channel that the water is moving through, but it's also the surrounding terrain that contributes to the water of the stream. So it certainly includes the valley bottom, but it also includes the sloping walls and where water flows downhill into that stream. The top of those stream valleys are generally much broader than the channel width because of mass wasting. We talked a little bit about that, but stream valleys are divided either into narrow V-shaped valleys or wide flat valleys. And again, there's lots of in between, but those are the two general shapes. Now, the base level is the lower limit to how deep a stream can erode. And the base level is essentially the surface of whatever body that stream is flowing into. So if it's flowing into the ocean, then the base level is sea level. It's flowing into a reservoir, the base level is the level of that reservoir. And again, it usually occurs where streams enter another body of water. The velocity and the ability to erode are greatly reduced once that stream moves into that body of water. Sea level, again, is the ultimate base level. But there can be temporary or local base levels that can be lakes. Resistant rocks can create a base level, like a waterfall is because there's a resistant rock and the water falls over it. Once it breaks away that resistant layer of rock, it will erode right down to that waterfall. But for a temporary time, even though it's maybe a very long time in human scales, that resistant rock may create a temporary base level. And if base level changes, then streams will change. Think about water running down into the ocean. If a glacial period ensues and much of the ocean water is locked up in ice, sea level will drop. That will mean that your base level will drop, and then you'll see a change in the stream and how it erodes. And so changing of a base level can cause readjustments of a stream. Here is an example of an artificial change in base level. We've got stream flowing down to the ocean. It has adjusted to its base level, and then you put the dam up, and now it's got a higher base level, so the water begins to slow down more quickly and dumps its sediment, and you can see where it's literally changed from its original profile to a higher profile because this reservoir has been created, this new base level. If you took this dam away then and it began to rush back down to the sea, it would cut back down through that new profile and make a nice wide channel. So typically what we find with down cutting of these stream valleys, it's going to be dominant where you have a steep gradient, and when the channel itself is above base level. Once the channel gets down to base level, you're not going to see down cutting anymore. It occurs through abrasion, which is those rocks and pebbles bouncing along the stream bed, just cutting away at that stream bed, and it typically produces these V-shaped valleys with steep sides and rapids and waterfalls. Downward erosion becomes less dominant as a channel reaches that base level. As it gets closer and closer to that base level, you're going to see less and less downward digging and more lateral side-to-side digging. The channel becomes a meandering channel. So we may have started out, this is the whole view right here, where base level was way down at the bottom, and this new channel and stream is cutting down, and as that gets down to, it's closer to its base level, we're going to see it become more meandering, and eventually you're going to get this well-developed floodplain. Now, what we have in this well-developed floodplain is erosion going on the outer sides, right? Deposition, the point bar going on here, so you have a cut bank on this side, deposition, and a point bar on this side, and you can see as the meanders not only go side to side, but they move downstream. We've got a cutoff here, so we have an oxbow lake. A cutoff here, we have an oxbow lake, and there's some other interesting landforms that we're gonna learn about a floodplain here in a couple of minutes, based on this whole flooding and then low water level type of periodicity that we see with floodplain. There'll be periods of high rain and flooding, and then more arid periods and less flooding. So let's first talk about different types of meanders and different types of terraces that are created in this floodplain. An incised meander flows in steep, narrow valleys. So these are meanders that develop when the stream is near base level, but the base level falls and the stream starts down cutting again. And so what happened is you've got a stream and it's near its base level, it's meandering, it's all happy back and forth, and then let's say the base level falls because of glaciation and sea level falls. Then it's going to begin to literally cut through its floodplain and create an incised meander. This can happen because of sea level fall, as I mentioned, but uplift, as in the Grand Canyon. The whole Colorado Plateau is uplifted, and the Colorado River had to incise down into to get back down to base level. Because of a relative drop in base level, the river begins to erode downward to the previously deposited alluvium. So this is, as you can see, that's the valley. This is previously deposited alluvium from previous floods. Now it's cutting down through that, and its valley's probably going to narrow a little bit. So you're going to get these old alluvial deposits that are going to remain, and they're going to create these terraces, and we call them stream terraces. They are the remnants of the former floodplain. That's the old floodplain way out here. This is the new floodplain, and the remnants of that older floodplain are these flat areas of deposit of alluvium that become stream terraces. Streams, of course, transport sediment and deposit it downstream. They deposit it just like on the meanders, the point bars on the inside of the meander. Any place that alluvium or sediment's deposited is a bar. Bars are deposits of sand and gravel, generally temporary, like sandbars at the beach, and can be carried away to the ocean, or in case of sandbars, by the ocean. Some longer lifespans of some depositional features are deltas and then natural levees. So The deposition of sediment, the deposition of alluvium can result in bars, which are temporary, but also result in deltas, which are not quite permanent, but closer to permanent, certainly on human timescales, and then natural levees. Deltas form where streams enter still bodies of water. So a delta forms where a stream enters its base level. Flow decreases, sediment falls out, the delta grows outward, and the gradient lessens. Now eventually, because the gradient lessens as the delta grows outward and things slow down, more and more sediment is deposited in the stream channel and it gets choked off, right? And that causes that stream channel to want to find a different route to the base level. It will begin to create these distributaries, and these distributaries effectively carry water and sediment away from the main channel. So this bottom is what it looks like. So here is the stream, it's extending out into the base level and it's dropping its sediment, but eventually this, because the water begins to slow down, gets choked off and the water has to find a different route. And then this may get choked off here and the water finds this different route and that different route. And as different channels get distributaries, as they're called distributaries, they distribute the water to the base level. As they get choked off, these triangular shaped deltas, which is why it's called the delta, triangular shape, form, and oftentimes are called bird's feet deltas. Now, as we look at the delta over its life cycle, it actually creates some fairly interesting beds of sedimentary deposit underneath the delta. So you have to remember the delta starts way back here at the edge, right? That's where it starts in the very beginning. In the case of the Mississippi Delta, which is 6,000 years old, you have to go back and say, well, this is 6,000 years ago. So 6,000 years ago, when the river came into the Gulf, it first deposited, as it moved into the Gulf and began to slow down, it deposited way out far away the very, very fine-grained sediment, right? This is the very fine silts and clays, and that's called the bottom set bed. And it extends from where the delta began at its very beginning well out into the base level. In the case of the Gulf of Mexico, tens or maybe even in some cases more than 100 miles out. Then as that delta grew, that meant that further and further and further away, further and further and further out in the delta, water was moving more quickly as it was moving through the delta, and so then larger, more coarse particles began to fall on top of that first bed that got laid down, nice and flat. And then this occurred as it got, the delta went further and further out, the larger particles were dropped, and it created this foreset bed. Now, this last bed, very thin, that extends out part of the way, this bed of sediment actually gets deposited when you have major floods. The floods actually, cover the entire delta, and that bed gets laid down. Now, the Mississippi Delta has been going on for 6,000 years. Number 7, there's been 7 different deltas. Number 7 is where we are now, this nice bird's foot delta. But essentially what we know is that in the very beginning, the delta was here, and then the river found a different route to the base level, and the delta was created here. So this is when the delta was only this big, and the delta was this big, and then it found a new route, and the delta was that big, and then it found a new route over here, and the delta was that big, and then a 5th route, and then a 6th route, and now we're on the 7th delta of the Mississippi River Delta, and this last one is the work of about the last 500 years. Now, we talked about the different landforms that streams deposit, bars, deltas, and I said natural levees. Natural levees are built by successive floods on rivers. So if this is the channel, and so here's your whole floodplain. We're looking at it from kind of a bird's eye view, not maybe a side view, but here's our side view. This is the channel. The water is normally right in this channel. When a flood occurs, that water pushes out over the banks and it moves out into the floodplain. Well, the faster moving water begins to slow down almost immediately, and so coarser sediments are dropped right next to the channel edge. And over a period of time, and of course, so the flood occurs, coarser sediments are dropped here, finer sediments are dropped out there, which is great. That's what makes great agricultural land out here, those fine silts and clays. Then the flood recedes, and there's a small little levee. And then your next flood occurs, and you get more coarse sediment, and the flood recedes, and there's a larger levee, and subsequent floods actually create these natural levees. Another interesting thing it does is by depositing a lot of clay and silt back here on the edge, it creates a layer that's not very permeable to water. So you tend to get swampy areas on the edges away from the main channel, refer to those as back swamps. And because this delta is here, if there's a river that's trying to flow down into this, a tributary of this main river, if it encounters this natural levee, the natural levee is right in here, well, this little river here can't get to the main channel, so it actually flows parallel. It's called a Yazoo tributary. It will flow parallel to the main channel until it can find a place to break through and get into the main channel. So floodplains, like deltas, have their own unique landforms that are largely a function of flooding and receding water. And of course, a flood occurs when stream discharge exceeds channel capacity, and they are literally, because as I said, moving water is the strongest force in nature. Some of the most devastating natural disasters. Most floods do occur from weather, snowmelt, or heavy rains over large areas. You have flooding that you think of like along the Ohio or the Mississippi, then you have flash floods that have limited geographic extent, but that's because of super intense rainfall or surface conditions, not only like streets and roadways where water can't run off, but also steep valleys out west in arid regions where the water doesn't percolate into the ground well, and that topography channels that water, and you get massive flash floods that can rush down a valley, and you won't even know it's coming because the water, the rain is actually happening up in the mountaintop, and it comes down and can wash right through a valley. Flash floods, extraordinarily dangerous. Now, there are ways to attempt to control floods. You have levees, you have dams, and channelization. So artificial levees are just like the natural levees, just big earthen mounds. They're always much deeper, much higher. You put them along the stream channel, and that should allow the channel to hold more water. Flood control dams, you put a series of dams along a channel, and you hold water in those reservoirs and only let it out at a steady rate or a lower rate so it doesn't flood downstream. Problem with flood control dams is behind those dams, sediment deposits in the reservoir instead of flowing downstream, and eventually the reservoir can't hold as much water and they lose their effectiveness. Artificial cutoffs is where we actually take those meanders and create artificial cutoffs between them, and that allows the water to run straight down the river, moves more quickly, and it moves out into the base level more quickly. And so you don't have as much flooding. There's also flood control channels where we move water away from the main channel, maybe around urbanized areas. Most scientists are beginning to think that non-structural approaches may be the most efficient, which is actually just not building in a floodplain. All right, from flooding, we're going to move on to groundwater. Again, channels and rivers occur because water is moving over land. Groundwater is where water moves beneath the surface. It exists in the tiny pore spaces between grains of soil and sediment, but it also exists in the narrow joints and fractures in bedrock. So you can have groundwater moving through unconsolidated sediment, but it also moves through bedrock, through the joints and the fractures in that bedrock. And it also moves through lots of other solid rocks, particularly sedimentary rocks where there's plenty of pore spaces. So groundwater is the largest reservoir of fresh water readily available to humans. And of course, overuse, depletion, or pollution, that's a major problem for groundwater, right? All right, we talked about this at the beginning of the chapter. Groundwater is the largest reservoir of fresh water readily available to humans. Of all the fresh water in the hydrosphere, 68.7% is in the ice sheets and glaciers, and so 1.2% is going to be in surface and other fresh water, and that adds up to get around 69.1%. 30.1% of all the fresh water available is in groundwater. So it's a very important resource, and it's kind of always been thought of as maybe a renewable resource, but maybe we need to begin to think about it as non-renewable. All right. Why is groundwater important? It stabilizes stream flow, meaning groundwater feeds streams. If there's no rain falling into the stream, groundwater is what feeds it. It's also very important because it's a massive erosional agent, eroding out massive caves, but also, as importantly, eroding out massive aquifers. And here's some erosional landforms, big sinkholes spread across this entire region. Groundwater comes from the infiltration of rainfall into the ground. Right? So the amount of infiltration into the ground is influenced by the slope, the surface material, the intensity of rainfall, the type of vegetation. We talked about that before. There is in the ground, just below the surface, a belt of soil moisture. That belt of soil moisture is in the soil, that's the top, the very top. It's a film of water on soil particles. So if you've ever heard of surface tension, why can a spider walk across a swimming pool? Because of the unique properties of water, adhesion and cohesion, water sticks to itself, it sticks to other things. It has surface tension. You can have a drop of water dangling from your fingertip. Why doesn't it just fall off? Well, surface tension is holding that drop of water there. A drop of water on the table, why is it a little tiny lens, little dome shape, not completely flat? Well, it's surface tension. It's all surface tension. So surface tension holds a tiny film of water on soil particles, and it can't be pulled off those soil particles. Now, once you get down through the part of the soil that's just moist or has some water in it, eventually you're going to get to what's known as the zone of saturation, and that's when all of the pore space in the ground is filled with water. The upper level of that zone of saturation is the water table, and it got that name because it's flat, but in reality the water table is not flat at all. The water table actually, particularly in times of decent rainfall, follows the topography of the land. The area above that water table, between the water table and that soil zone, is called the unsaturated zone, and that's what this looks like. So here's our saturated zone in light blue. That is the main water table. And we don't have a serious topography change here, but the water table gradually goes up over this hillside. Here it gradually goes up over this hillside, and so water that percolates down here will go down that hill and then recharge that stream. Water that percolates here will eventually go down this hill and recharge this stream. Or maybe it comes out in the form of some springs. But nonetheless, I think it comes out here in the form of a spring, here in the form of a spring. Water flows downhill. Just like in a river, it flows downhill. In the ground, it flows downhill. It just flows extraordinarily slowly downhill. So in the zone of saturation, all the pore space is filled with water. In the unsaturated zone, there's a film around the sediment or the solid rock particles, but that film of water can't be extracted or moved. So this is not a good well. And this is a good well, but this is an interesting situation because there's this confining layer. So this is going to be a layer of strata, a layer of rock, or maybe even clay, something that water doesn't move through. It can be something that holds a lot of water. Clay holds a lot of water. Have you ever played with dry Play-Doh? No, of course you didn't, because it was dry. Clay and Play-Doh has to be moist, has a lot of water in it. But water doesn't move through it. That's why we have clay pots. Water doesn't move through it. So in this situation, rainfall here gets trapped by this confining layer, which is known as an aquitard, and it creates a little water table, a lens of water right there, which is known as a perched water table. So, unsaturated zone, saturated zone, water table, springs and rivers are literally where the land surface intersects with the water table. If the land surface came up here, was a mound right here, there'd be no stream. The land has to intersect with the water table in order for there to be water. Here, the land is intersecting with that water table. All through here, the land is intersecting with the water table of this perched water table. And that's how you get those springs with water running down into that stream. As I said, water table is irregular. It's a subdued replica of the surface. It's highest below hills, lowest under valleys. And the reason why is because groundwater moves so slowly. So if it rains on a mountain, that water is going to flow down into the mountain, and it's going to take a while for it to eventually flow down to the water table. So sure, if you have ongoing rain, your water table is going to be high under the hills. Now, if it gets really, really dry for a really, really long period of time, maybe that water table under the hill will begin to settle down closer to the flat water table. But generally, it's a subdued replica of the surface. How do we get water out of stone? How do you get blood from a turnip? How do you get water out of rock? How do you get water out of an unconsolidated sediment? It depends on its porosity, and it depends on its permeability. Porosity is the percentage of total volume of rock or sediment that consists of open pore spaces, the spaces between particles, in joints, in faults, and in cavities that have been dissolved, or vesicles. Remember vesicles, that's those little air bubbles when magma cooled very quickly. Porosity depends on the size, the shape, the packing, and the sorting of grains. If you have lots of different grain sizes, you may have one type of porosity. If all the same grain size, a different type of porosity. But in unconsolidated sediment, that porosity can be as much as 50%. So this beaker has 1,000 milliliters of sediment, all right? And this has 1,000 milliliters of water. if you were to pour that 1,000 milliliter beaker into this 1,000 milliliter beaker of sediment, it would become full of water when about half of the water has been poured in. That tells us 50% of that sediment is pore space. 50% of all that is actual pore space. It looks like it's solid, but it's not. 50% is pore space. So that porosity is at 50%. The other factor that we look at is permeability. And permeability is very different than porosity. Permeability is the ability of water to move through pore spaces. There may be lots and lots of moisture, like in a clay layer. You could have a thick clay layer that has tons and tons and tons of moisture. The question is, will it move? Well, it won't move through a clay layer. So permeability is a material's ability to transmit fluid. How well does the fluid move through that material? If the spaces are too small, water can't move through. If the spaces aren't connected, water can't move through. So materials with very low permeability, again, are aquatards. And materials who have tremendous amount of permeability, something you can actually get water out of, those are known as aquifers. So groundwater moves slowly from pore to pore. The typical rate is a couple centimeters per day. It moves from high water table down to low water tables. Water table comes up over this hill, water goes in, it goes down to that water table. Now you may see here that it's going up against the force of gravity. The reason why it's going up under the force of gravity is because all this water above it is pressing down, and the looping lines result from the downward pull of gravity and the tendency of groundwater to move toward areas of reduced pressure. So gravity is pulling it down, but there's more pressure here than there is here. There's very little pressure here, so it moves toward an area of reduced pressure. As I said, a stream or a spring is where the water table intersects the surface of the ground. So in the case of this spring here on the side of this cliff, it's probably something like this. There's an aquitard at this layer right here. Water that's percolated down from this rock gets that aquitard. It can't move down any further, so it moves laterally, and it moved laterally until it broke the surface, and then it flows out as a spring. So a spring is a natural outflow of groundwater. It occurs where the water table intersects the Earth's surface. Aquitards prevent the downward movement of water. You get this perched water table, a localized zone of saturation above the aquitard. The water moves along that aquitard toward a place where the Earth intersects, and that's where you get a spring. A well, of course, is when you drill a hole, right? Drawdown is the lowering of a water table in a well. If you pump and pump and pump and pump a well, you may begin to draw it down. If you pump more out than is recharged by rainfall, you're going to get a cone of depression, and that's what your cone of depression looks like. Now, most residential wells barely have any depression at all, but a serious well, maybe for irrigation, can get a serious cone of depression. And if you have a bunch of serious wells and you have a lot of cones of depression, the entire water table can be pulled down, and that can be very dangerous. It can result in depletion of the water table. All right, have you ever heard of an artesian well or an artesian system? That is where water flows freely from an outlet that's far above the water table. A spring, you have to have the Earth's surface intersecting with the water table. In an artesian system or an artesian well, groundwater will flow freely well above the water table, and it's because you have a confined water table. A couple of things you need to have this confined water table. The aquifer itself has to be inclined, and you have to have an aquitard above and below the aquifer to confine that aquifer. Because of the incline, water that flows into the upper levels of the aquifer, where it's exposed, creates pressure at the lower levels of the aquifer, and it's that pressure that pushes the water out as an artesian well. And here's a pretty typical view of an artesian well, and you can see that at number 1, where that well is at number 1, that's very close to a recharge area. And that recharge area is where our aquifer, so this blue stripe right here is our aquifer, all right? This dark gray stripe, that is an aquitard. This dark gray stripe is an aquitard. Well, what could that be? Well, it could be shale, it could be slate, it could be just clay. Lots of different things create aquitards, all right? That recharge area, that water flows down into the aquifer and it fills up, just like a glass of soda filling up around the ice. It fills up, it fills up, it fills up. That is the water table there. So because water is pressing down on this confined aquifer, it will be pushed up to the water table. So this is a non-flowing artesian well because you dug a well, it got pushed up, but not all the way up. This is a flowing artesian well, like we see here in this example, because the ground is literally lower than the water table. That's the water table, that's the pressure surface right there, and the ground is lower than it, so the water actually flows up and out of it, as you can see here. So artesian wells can be found in different parts of the world, including in Florida. Now this is kind of an artificial artesian well. We get a water tank, we pump water up into it, and that's literally the top of the water table. And so if you're in a house very close to that water tower, that water tank, you're going to have some serious water pressure. But let's say you're miles and miles and miles away, and maybe even up on a hill that's up closer to here, well, you're going to have a whole lot less water pressure unless you actually have a pump. So we mentioned these aquifers, and again, they exist both confined and unconfined. So this is a confined aquifer, but let's just say we have this aquitard, this non-permeable layer below, but completely permeable above. That would be an unconfined aquifer. Anything that rained here would infiltrate into that unconfined aquifer. So aquifers can be confined, they can be unconfined. The High Plains aquifer, making up a big part of western Texas, Kansas, Nebraska, even parts of Colorado and Wyoming and South Dakota. It's also called the Oklawaha aquifer. This part of the world is actually fairly dry. Okay, you don't get a lot of rain in Wyoming and in northern Colorado. Or even western Texas. It's just deserted, not quite deserted, but it's an arid region. So how do we do all this agriculture? Well, we do it with pumping out of the High Plains aquifer. The pump is in the middle, the well is in the middle, and this is the area that is being used for agriculture. Well, over pumping, as I showed you, can draw down that water. And if you're talking about a landform that's not on solid rock, but it's on like unconsolidated sediment like we have in the San Joaquin Valley, if you over pump the aquifer, that sediment is just going to settle. And from 1925 to 1977, the pumping in the San Joaquin Valley created subsidence, which was just the compaction of sediment because there's no longer water to hold it up. It caused the San Joaquin Valley to subside that far. That's how far it subsided between 1925 and 1977. Not really very funny, but very serious. And again, it's where areas are underlain by thick layers of loose sediment because that loose sediment is held up by all that water. You pump out all the water, the sediment just compacts down and you get subsidence. All right, so overpumping is a problem with groundwater. You can also have contamination of groundwater. Septic tanks, sewer systems, farm waste, it's all bad. Interesting thing about water moving through an aquifer is it will be purified by natural processes when it moves through a good aquifer like sand or some kind of permeable sandstone, something with really small pore, really small sediment size. As the water moves through very, very slowly, that sediment will actually pull the contamination out. Unfortunately, if you're like in Florida, where the aquifer is just a big limestone aquifer with lots of big spaces, it's just going to move so quickly and it's not going to touch enough sediment that it basically is not going to be cleaned out. So here's a Florida situation, limestone overlain by sand and clay. If you have a leaky septic tank here, that water is going to flow very, very quickly. In a well dug here, it's never going to have a time to clean that water out. Whereas if it's all this sandstone, that water is going to move very, very, very slowly, and over months or years, it'll be naturally cleaned out. All right, the other work of groundwater is the erosional work of groundwater. Most groundwater contains carbonic acid. So why is that? Well, when rain falls out of the sky, it's pure water. Raindrops are pure as the driven snow, pure water. But as they fall through the atmosphere, CO2 dissolves in them. And so when that water strikes the ground, it has a little bit of CO2 in it, which creates a very dilute carbonic acid. It's a very, very weak acid. I mean, milk may be more acidic than it. Certainly lime juice is. Nonetheless, it's enough to dissolve limestone. And in addition to just picking up CO2 in the air, as that same water that strikes the ground percolates through the soil and goes through decaying plants and animals, it picks up more carbon and becomes more acidic. It can dissolve limestone, forming caves and caverns and sinkholes in what we call karst topography, karst landscapes. This is the term for a landscape that is, the rock is easily dissolved. So caverns form due to the erosional work of groundwater. You get a zone of, and caverns typically form in the zone of saturation. So it's saturated limestone. All the pore space in the limestone has water in it, and slowly, or maybe even rapidly, that limestone is dissolved, but the water is still there. But if that water table drops for whatever reason, now you can have an open cavern. And that's the way that sinkholes form as well here in Florida. You may have a cavern just below the surface that's full of water, but if that water table drops, that cavern becomes open, and if the roof of the cavern can't be supported, it will collapse and create a sinkhole. Now, it also creates these decorative features, the reason why people go down in caves, of stalactite and stalagmites. Essentially, as that water percolates to the soil and picks up all that carbon, once it gets into the air, well, some of that carbon dioxide dissolves out, comes out of the water, and that extra carbon then solidifies into calcite, calcium carbonate. And so this is what they call a little straw. The water is coming to the middle of it, and it gets down to the bottom, and that the air touching that water takes some of the CO2 out of it, and a little ring of calcium carbonate forms right there. It's almost imperceptible, but over, again, tens and hundreds and thousands and millions of years, you get stalactites. And where that water drops and strikes the ground, you get stalagmites. The other thing that happens in karst topography over a very long period of time is just the significant erosion. Here's a stream, but that stream erodes the limestone underneath it. The limestone in the water table gets eroded, and you start getting depressions and sinkholes and streams that disappear into sinkholes, and then on the sides of this mountain you get little springs. You just get karst topography, all right? And this is very similar to what we have in Florida, Tennessee, Kentucky. Have you ever been to Mammoth Cave in Kentucky? Well, if karst topography goes along long enough, this is a landscape that was, all the limestone was up to the top of these towers. But over time, differential dissolution of that limestone created these amazing karst towers with these very steep-sided hills. And here's a pretty typical Florida sinkhole. This picture actually taken in Florida. So that was Chapter 3 from An Introduction to Earth Science from the textbook Foundations of Earth Science by Lutgens and Tarbuck. Of course, Chapter 3 was from Landscapes Fashioned by Water. So next, coming up, is going to be Chapter 4, and Chapter 4 gets into both glacial and arid climates. So we'll see you then.